Welcome back. Likewise, the ratio of static properties, we can derive the ratio of stagnation properties as well. We have seen that across the normal shock wave, the upstream and downstream stagnation temperature remains constant due to adiabatic character of the flow across the normal shock wave. However, due to the irreversibility, the pressure loss always occurs while the flow being supersonic or hypersonic upstream of the shock wave, and when it becomes subsonic downstream of the shock wave. Then the stagnation pressure loss, we can, if we see that the downstream pressure at the downstream side stagnation pressure is PO2, and upstream side if it is PO1, the ratio of stagnation pressure PO2 divided by PO1, we can obtain something like this using algebraic manipulation. We can divide PO2 by P2, and since in the numerator by multiplying again P2 by P1 and then further P1 by multiplying, and then we can have this ratio P1 by PO1. What we essentially see here, PO2 by P2 we can write down using the isentropic relation for the downstream side, which we can write something like this: m2 square to the power gamma upon gamma minus 1. And likewise PO1 divided by P1 we can write down 1 plus gamma minus 1 by 2 m1 square and gamma upon gamma minus 1. Whereas m1 and m2 we can replace using what we have already derived the function of m1 expression. Using all these expressions, if we insert here and static pressure from P2 by P1, we can use the expression of this. Then all these expressions when they combine leads to such a big expression of PO2 by PO1, that is the stagnation pressure ratio across the normal shock wave. Now moving to further, if we calculate the change of entropy of the flow incurred when traversing across the normal shock wave, then we can calculate from isentropic relation which we derived S2 minus S1, which is indeed delta S, can be written as Cp ln T2 by T1 minus R ln P2 by P1, and we are aware of, we have already seen P2 by P1 and T2 by T1 expression, which we can write down something like this, or it also can be written, that is Cp ln PO1 by PO2. Introducing PO1 by PO2 from the previous slide, we can insert this expression into this, and then we can develop this expression of S2 minus S1 by R, that is delta S by R. One can see that when Mach number, that is the upstream Mach number, which is this expression is a function of upstream Mach number, we can readily see that when m1 is greater than 1, all this expression leads to the phenomena, that is delta S by R is greater than 0. That is, the flow across the shock wave, normal shock wave, comes out to be irreversible. That is, here also one more thing we would like to mention here, that in doing so, this activity, that while proving that delta S by R greater than 0, we should note that gamma is not a wide range parameter. The gamma from monatomic to polyatomic gases, the range of gamma is 1 gamma and 1.67, that is for monatomic gases, and then for near to polyatomic gases closer to 1. Hence only m1 is the dominant parameter based on which the delta S by R can be calculated, and we can see here that when m1 is greater than 1, the delta S by R is greater than 0, that is, this process is possible according to the second law of thermodynamics, whereas when m is less than 1, this expression is indeed negative, and then we say that this process, that is from a flow from upstream to downstream, if in doing so, if delta S by R is negative, this is an impossible process, and this is eventually telling that when the upstream Mach number is subsonic, a shock wave cannot be generated. This is mathematically proved from this point. Now, moving to further, we can say always this statement, please remember that supersonic flow across the normal shock wave becomes subsonic flow. That means a subsonic flow, inside a subsonic flow, a shock wave can never be generated, which is a violation of second law of thermodynamics. Now, we will apply this normal shock wave phenomena, which is usually seen in the CD nozzle, that is a convergent divergent nozzle. In our discussion, we have seen it that a typical convergent divergent straight nozzle looks like something like this. In this kind of nozzle, the upstream flow, which is coming subsonic, leads to a supersonic flow at downstream side, that is exit of the nozzle. The M which is exiting the flow is subsonic, while M entering it is subsonic flow, and this is our throat section. Now, let us see here this important figure which we must discuss at this point, that if this is a contoured convergent divergent nozzle shown in the above, and downstream side and the below side we are plotting here, the x is the axial coordinate location in the along the nozzle length from this point, and we are interested in having a ratio of P by P naught, where P naught is the upstream chamber pressure or reservoir pressure, which is held constant, and now P is the pressure which we are measuring in this nozzle, inside the nozzle, from entry point to exit point, and the profile looks like something like this. One more point here, that the governing pressure force at the downstream side is termed as PB, that is also termed as back pressure. The back pressure is the controlling pressure through which we start the flow inside a convergent divergent nozzle. Due to that back pressure, various exit pressures are shown here in this graph, the PE1, PE2, PE3, PE4 and PEC. These exit pressures are occurring or obtained at various back pressure subject to the condition which we are discussing. Now, when the back pressure, this PB, is equal to the stagnation pressure, then no flow will occur inside the convergent divergent nozzle. However, slight decrease of this back pressure will fetch, let us say, few streamlines inside this nozzle, and flow starts taking place, and then we will obtain a flow condition here. That graph, that process is shown by the uppermost line here, where let us say we are obtained by some decrement of back pressure, decrease in back pressure, we have obtained a state PE1, that is exit pressure 1. Now, what we see here, if we see the throat here, then this line represent PT by P naught, this dotted line is represented by PT by P naught. In this condition, what we see, the throat here is having a pressure called PT, let us say throat pressure, but still the entire flow here, being a convergent portion, the velocity increases according to the Bernoulli's equation, incompressible Bernoulli equation. Now, the decrease then increase in velocity will cause a decrease in pressure, and that is why we are obtaining a decrease in profile, non-dimensional profile P by PT by P naught, something like this. However, as soon as we reach the minimum area location, that is throat here for this convergent divergent nozzle, when we start diverging means the flow meets the divergent portion, what we essentially feel that since the flow is subsonic here, when as soon as the divergent portion comes, then this portion start acting like a diffuser, and hence the pressure will again increase. Now if we decrease the back pressure to a limit, let us say here I am decreasing PB1. Now in this case, if the back pressure is decreased to PB2, in this case some more streamlines they fetch into the nozzle, and then we have obtained a condition again citing the similar reasons, that is the first decrease in pressure and then further increase in pressure, because this portion, divergent portion, acts like a diffuser, and hence we get the state something like PE2. Now in doing this exercise, if we keep on decreasing the back pressure from PB1, PB2 to a stage comes, let us say PE3, and there is a state also PEC. But now first look at this zone, that is from entry of the convergent portion towards the throat. What we here see here, that this orange color line which is shown here is denoting here a point here where P by P naught is exactly 0.528 for a perfect gas. Now this 0.528 is, please note, the fluid which we are discussing is here air, which has the gamma 1.4, that is the ratio of specific heats. Now evaluating from isentropic relation of P naught by P and reversing that, we obtain 0.528 when the pressure ratio Pt by P naught comes to this place. What we essentially finds that this throat becomes choked, that is a sonic condition, that is a sonic Mach number or Mach 1 is obtained at this point. As soon as the throat is choked, then we see essentially two arms, one blue color and another one a green color arm, we find it. What are they? Please note, so far we are interested in controlling through back pressure, which says that Pb by P naught is varying something like this when the throat is, in these two cases, are not choked. However, as soon as the throat is choked, that is the sonic condition, that is the Mach 1 is obtained at this place, then if the Pb or Pb3 is, if this pressure is more than the throat pressure, the upper arm is received. That means even though we have achieved a state of sonic condition at the throat, but in the divergent portion, if the pressure is more than throat pressure, a subsonic arm will be obtained, which is denoted by blue color. Whereas when this Pb is something about PEC, a correct pressure, then a supersonic arm is obtained, which is isentropic supersonic form is obtained, shown by green color, and upper arm is the isentropic subsonic arm, that is there are no irreversibility is obtained inside this divergent portion. Now what happens when the pressure is lying, this back pressure is in between PE3 and PEC? At this stage, please note that all these PB1, PB2, PB3 are equal to PE1, that is the pressure just at the exit, at the second case and the third case. Similar the case is that here let us say PB correctly expanded. This PB and PEC are equal here, and all these cases they are equal, whereas the back pressure between these two limits of a subsonic isentropic flow and a supersonic isentropic flow, in these two cases the back pressure is not automatically equal to exit pressure. To have this pressure equal, nature has provided that in between these two limits, a non-isentropic solutions are obtained, and these non-isentropic solutions are taken as considered as in the form of a shock wave. For the analysis purpose, we can never ignore, we know that we can never ignore the boundary layer formation inside any duct, and same as the case with a supersonic flow inside a convergent divergent nozzle. That means if the full irreversibility or the vortices formation inside the boundary layer we are considering, then the whole flow in supersonic in the divergent portion of this convergent divergent nozzle will be irreversible. However, a model, the flow is modeled such that all the losses incurred in the divergent portion is taken considered in the form of a shock wave, such that the complete flow upstream of the shock and the downstream of the shock is still isentropic, except the flow across the shock wave. That means in between these two limits of PE3 and PEC, when the back pressure is in between these two limits, a shock wave suddenly appears in the divergent portion, and it is modeled such that to have a complete isentropic flow except the location of the shock wave, all the irreversibility losses are merged in the normal shock here, and hence the other complete flow upstream and downstream is taken as isentropic. Now, what happens as soon as you decrease the, let us say, a pressure called PB4, the back pressure, to a stage 4, you decrease from PB3. When it goes further, then what happens, the shock wave suddenly appears somewhere like this, and since across the shock wave which is standing somewhere here, now across the shock wave, whatever the supersonic flow obtained in this length is crossing over the shock wave, normal shock wave, and becomes subsonic in this zone. And since the subsonic zone, the subsonic flow is obtained in this divergent portion, then as soon as it meets a diverging passage, a subsonic flow again start decelerating, and in turn pressure increases, and that is what obtained by this dotted line. You decrease the back pressure further, let us say PB 4-5 case. In this case, when you decrease further, what happens, there is a stage comes here that due to decrement of the back pressure, the shock here start moving forward, and that is what exactly shown by this purple color PE4, and then we have written shock, that shock is standing at this location. That means in the divergent portion the shock is moved. Now you keep on decreasing the shock, the back pressure, then the shock will travel downstream side further. Now there comes a stage where shock is just standing at the exit, and that location is PEC. And now when this location is obtained, what we see throat onward up to the exit portion of divergent portion of convergent divergent nozzle, the total isentropic flow conditions are obtained, and this is called a correctly expanded supersonic isentropic flow in the convergent divergent nozzle. One more point here, please note that as soon as the throat is choked, even by decreasing the back pressure, we are able to move the shock further downstream. However, note that the mass flow rate was constant, which has been governed as soon as the sonic conditions are obtained here. That means decrement of back pressure will naturally cause the travel of this normal shock wave from one location towards second location towards the exit side, but the mass flow rates remain unchanged for a given stagnation pressure. Now this graph again we have experimentally plotted here. What you see here, that we have measured from a convergent divergent nozzle of something like this, and by various ports, pressure ports, that is, and pressure ports are formed here at various locations and at the wall, and the ports the pressure is measured. In doing so, what we find that inside the convergent portion of convergent divergent nozzle, in this convergent portion the flow is subsonic, and hence we are essentially finding a constant pressure profile. Whereas as soon as the throat conditions are choked, what we are obtained here, from here onward the sudden decrease is in pressure, whereas because the flow is accelerating while till the meeting of normal shock wave, let us say first is the blue color one, where we have represented a nozzle pressure ratio P and PR, that is defined nothing but in experiments as back pressure divided by the running stagnation pressure, PB by P naught. And if this is 3, then in that case, which is represented as blue color line, you can see here after this point, that is the location wise, we can mention something about 0.58 x by L, which is again a non-dimensional, or I can say 0.58 times length, if L is the total length of the nozzle. In such circumstances, what we find here, that from here onward, as soon as the flow meets the normal shock wave, it becomes subsonic, and hence in the divergent portion all other pressure ports we are obtaining a subsonic flow. Likewise, the pink color, we can say when you have the controlling pressure, that is PB by P naught 4, then again what we find is shock wave moves further, because NP4 is a further decrease, shows a further decreased pressure than NP3. Likewise NP5, NPR5, NPR6, NPR7. And there comes a stage, you please see here from the asterisk which shows the NPR7. After that a stage comes where the pressure is decreased so much that PEC, that complete isentropic solutions is obtained without the shock wave. At this pressure, the shock is just standing at the exit away from the pressure port, which is not reflected in this profile. And hence what we can see here, from the subsonic to supersonic side, all these graphs represent that the flow has traversed or flow past across the shock wave, move across the shock wave, and hence these profiles are obtained. So what theoretically we discussed here, we have experimentally found the similar condition during the experiments. Now the two most important point here, what I mentioned here, that the controlling pressure at this stage PB, which is a controlling pressure, and hence because of this the various exit pressures are obtained. What we essentially seen, that when the back pressure is equal to the exit pressure, we say this is a completely isentropic solutions. In scientific terms, this is also termed as correctly expanded flow, that is nozzle, convergent divergent nozzle, or in abbreviation CD nozzle, is operating under correctly expanded case, and this is denoted by exit pressure is equal to the back pressure. What happens when the back pressure is more than the exit pressure, or the back pressure is lesser than the exit pressure? The back pressure is more than the exit pressure and it is lesser than exit pressure. These two flow states are also termed as when the back pressure is more than the exit pressure, or vice versa, when the exit pressure obtained is lesser than the back pressure. In this condition, let us say if this is a convergent divergent nozzle and the obtained exit pressure here is lesser than the back pressure, then since the law of thermodynamic equilibrium says that the pressure coming out exiting the nozzle must be in the mechanical equilibrium as well. That is, there should be a balance of pressure, that is the imbalance of pressure cannot exist. Under this condition, the shock wave which is appearing outside just at the exit in the correctly expanded case moves such that in the form of oblique shock, something like this. The standing normal shock will convert a oblique shock, something like this, because due to the oblique shock properties, the pressure here will increase because we are discussing the static pressure, and since the pressure will increase and it becomes that this exit pressure which is lesser than the back pressure will actually increase the pressure and make it just as equal to Pb, and hence this condition where exit pressure actually less than back pressure and leads to an oblique shock formation at the nozzle exit is termed as overexpanded flows. Likewise, when the exit pressure is obtained such that it is higher than back pressure, then the nature has given another tool in the form of expansion fans, which has the property that it relaxes the flow condition, that it relaxes the pressure. That means, if the exit pressure is more than the back pressure, then instead of shock waves, expansion fans are formed, or something like traveling like this. And this, when the flow encounters these expansion fans, it relaxes the pressure, that is the pressure at the exit try to maintain an equilibrium with Pb, and finally the pressure downstream of the expansion fan will be just right equal to back pressure at that case. And this kind of flow situation where nozzle is operating such that expansion fans are formed at the nozzle exit, they are termed as under expanded flows, or this is a case of under expansion. Now, this we just discussed here, that the flow overexpanded when the exit pressure is lesser than the back pressure case. Here that exit pressure is more than the back pressure case. When they are equal, we say correctly expanded case. Now, this can be seen by flow visualization. Here I have brought an optical flow visualization technique, that is the Silurian technique. Please note that here, for the audience which are not familiar with the optical flow visualization techniques, from the basic fluid mechanics sides we know that any flow visualization, apart from quantitative measurement, qualitatively also the flow can be visualized, and we are aware of smoke flow visualization, tuft flow, oil flow. Likewise, the optical flow visualization techniques are three. They are categorized as shadowgraphy, second Silurian, and third is interferometry. These shadowgraph with optical flow visualization techniques, optical flow these optical flow visualization are characterized as shadowgraphy, Silurian, and interferometry. These visualizations of supersonic and hypersonic flow is based on the density change associated in compressible flow, and this density change is basically changes the optical properties, that is refractive index of the flow. And since the flow medium, the refractive index changes subject to the density changes, and hence these techniques are developed. Shadowgraphic technique says whenever there is a flow occurring where the density change is varying second order of spatial derivatives. That is, in Cartesian coordinate system, let us say x, y and z, if d2 rho by dx square or d2 rho by dy square or d2 rho by dz square in the Cartesian coordinate system, if the flow is sensitive to second order of density, then that technique is measured through pseudographic flow visualization. When the density associated density change inside a flow is sensitive to first order, that is d rho by dx, d rho by dy and d rho by dz, that is again the first order or first derivative, spatial derivatives of the density, then to have the minute details, because right now the flow is sensitive to the first order, that is more sensitive to the density changes. Therefore, to obtain more precise details of flow which is dominated by the waves, that is the shocks as well as expansion or compression and expansion fans, then that detail can be optically visualized by Cillerian technique. Whereas, when the density is directly sensitive to when the flow is directly sensitive to the density itself, then that kind of flow situation is visualized optically by interferometry technique, and that is a famous Mach-Zehnder interferometer. This kind of interferometry techniques are used for high altitude condition or in a rarefied atmosphere which is found in uppermost layer of the Earth's atmosphere. Now, where the molecules are having very separate identities and the density is very less over there. However, for the ground laboratory experiments or ground studies within the sensible atmosphere, both pseudography and Cillerian techniques should be used together to find out these kind of details. However, here I have brought here the Cillerian photographs for you to denote some properties which we are going to discuss here. At various nozzle pressure ratios, that is the ratio of back pressure to the controlling or reservoir pressure P naught, at various NPRs these kind of flow visualizations are obtained. Let us see how it happens. If you see here that the flow here at very low NPRs, where the back pressure is such that the flow is still subsonic, we see a jet coming out of the convergent divergent nozzle is something like this, which is a typical characteristic of subsonic flow. Whereas this second case, what we see here, this is a clear case of over expansion, because this is the oblique shock formation we see right at the exit. Whereas here we can see that a lot many expansion fans are formed at the exit, which travel further downstream, and shock also further travel downstream here. This is a case of under expansion. And now this is another NPR where the back pressure is decreased so much, we can see here strong expansion fans formation, that is the waves become stronger here. Now please note here, for this over expanded case and this under expanded case, there is a expansion fan formation. However, this NPR is of the case of correctly expanded flow, and this we must discuss at this point, that even though here the case of the pressure at the exit is less than the back pressure, and hence leads to the generation of oblique shock waves, whereas this is the case of exit pressure is more than the back pressure, and hence leads to the formation of expansion fans at the exit. Whereas even though the exit pressure here is equal to the back pressure, but still we find expansion fans formation, though we say this is a correctly expanded flow. How come? We will address this point in more detail here. Now what we have seen here, that in the first case, that when the normal shock at various locations based on the respective back pressure, we have moved the normal shock here, so that the entire convergent divergent nozzle here becomes isentropic. Now as soon as the condition becomes an overexpanded, underexpanded, or a correctly expanded, then this kind of structure of shocks, generally termed as shock cell structures, are formed. Shock cell structure. Now let us discuss what happens when this oblique shock waves which are coming out in the 2D diagram, 2D image like this, they are essentially 3-dimensional. However, as representation in a photographic image or schematic diagram, they are shown like a left running and a right running 2-dimensional waves. Now what happens, these waves in generally, when these waves come out, then they further move and meet at the just at the jet center line, that is a nodal axis at the exit, whereas they further travel downstream and meets the flow boundary, that is here we will term as a jet boundary. And from the jet boundary, since these boundaries are not real, and hence these waves which meets these boundaries, they undergo unlike reflection of waves and they become a expansion fan at this place, which further travels downstream both sides and again meets at the jet center line, and further they becomes and coalesce into itself and they become a oblique shock, and then the oblique shock further comes down and then again meets. From one meeting of the oblique shock to the second meeting of the oblique shock, waves are essentially termed as one shock cell. This is one shock cell. However, what we notice here, in this condition the oblique shocks are not meeting at one particular point, however with a gap of something like this, which is a dark color zone, or you can say a stronger waves, end points of a stronger wave. This end points or this wave where this oblique shocks are meeting, it is commonly termed as Mach disk. And it has been experimentally proved that whenever the exit pressure is lesser than or equal to 4 times back pressure, then this kind of Mach disks are generated from the experimental analysis. It has been already proved. These shock waves, when they further travel downstream and meets the jet boundary, undergoing the unlike reflection, and further, as I said, that these shock waves become expansion fans further become shock waves, and this phenomena repeats itself. That means using these kind of repetition by oblique shock to expansion fans to oblique shock generates a shock cell structure till finally the flow diffuses to the ambient, and this happens in the same in all the scenarios. However, when the shocks become stronger, what we see here, the waves become stronger, expansion fan or compression fans, then the shock cell structure length of shock cell structure is more than a lower back pressure cases. Where if we can see this thing here, in comparison to the overexpanded case, the shock cell structure or the waves strength of the shock waves are stronger in the under expansion cases here. However, before closing this discussion, we must ensure that why the expansion fans are formed here, whereas by mathematically this is a correctly expanded case. Note down that whenever the flow comes out from a confined passage of a convergent divergent nozzle and meets suddenly a infinite reservoir or ambient at the exit, then due to the relaxation of the flow, and even though the pressure imbalance is not present, due to the relaxation of the flow, a weak expansion fans are always formed just at the exit, and this expansion fans again meets at the jet boundary and converts into the shock wave, and hence a shock cell structure repeats, or you can see here that in the oblique shock overexpanded case 1, 2 and up to 3 visible shock cells, and correctly expansion 1 and 2 shock cells are still formed. A shock cell means the oblique shock meeting point at one location to another location, or expansion fan meeting point at the jet center line to the another meeting of the expansion fan jet center line. This 2 points in between the structure is termed as shock cell. Here in the underexpansion case, one condition is that still the flow relaxes, so expansion fans are naturally to occur. However, pressure imbalance is also present. These two supporting events of pressure imbalance makes the expansion fans stronger than the correctly expanded case, and then again the same phenomena of unlike reflection at the jet boundary or the flow boundary here takes place, and the shock cell structure repeats and such structures are formed. Now, we will take up one more important theorem which is termed as Rankine-Hugueniot relationship. This Rankine is important in terms that rather than the velocity, it is essentially denotes across the shock wave how the properties can be represented just in the name of thermodynamic properties, and the velocity and Mach number does not come into the picture. Rankine-Hugueniot relationship, basically originally it has been derived for a steady one dimensional flow of a combustible gas that burns to the completion, and equation relating to initial and final conditions are readily derived from the conservation equations. Now, if a pre-mixed flammable mixture in a long tube is taken, something like this in a long tube, and one end this is ignited, what happens? Due to burning of this combustible mixture, a flame front generates which travels downstream side, burning all the mixture here constituents. This flame, generally when the both tube ends are open, they travel approximately at 1 meter per second, and this kind of wave speed is governed by diffusion of heat and active radicals which are formed due to combustion. These waves which travels downstream are generally termed as, this phenomena is termed as deflagration, whereas if we close the one end of this tube such that this burning takes place, then is always a wave, a propagating wave, which is nothing but a finite strength compression front starts traveling from upstream to downstream location, and then this kind of waves enables the flow speed from subsonic to even supersonic level, and hence this supersonic wave formation is called a detonation. So, subsonic side deflagration, supersonic side detonation. Now, in detonation case, when the detonating wave, detonating supersonic propagating waves are generated, then heat and radical diffusions do not govern the flow speed or the flame speed or the wave speed. Rather, the shock wave structure developed in supersonic waves increases the temperature and pressure substantially to cause very high reaction rate and energy release that sustain the wave propagation. That means, in the subsonic case, when the burning takes place, the active radicals as well as heat of diffusion is basically a controlling parameter which controls the flame speed. However, once the one end is closed, where the burning is leading to a supersonic wave generation, that is the phenomena called detonation, the speed of this detonating wave is not governed by no more governed by diffusion, heat of diffusion and active radicals. Rather, the traversing of the wave increases the temperature and pressure that much that the temperature reaches to that level that sustains the travel of these waves further, and it leads to very high reaction rate as well. Now, in any analysis, though the waves are 3-dimensional in nature, but for 1-dimensional point of view, if we assume that this is a 1-dimensional steady flow, constant area passage, we are considering the flow inside a constant area passage, and a perfect gas adiabatic flow, that is the flow, the duct is insulated, no heat transfer with the surrounding, and again the assumption is body forces are negligible. Then we write the governing equation such that the mass conservation equation can be written as rho 1 small v1 is equal to rho 2 small v2, where we can see here the reactant or unburned gases, and this is a detonating wave is travelling, upstream velocity is small v1, downstream velocity is v2, and due to traverse of this wave, the reactants are encountered with very high temperature and they burned into the products. Now, across this wave, let us choose a small control volume where we are writing these governing equations. So, continuity equation readily gives you rho 1 v1 equal to rho 2 v2, whereas the momentum equation gives you p1 plus rho 1 v1 square is equal to p2 plus rho 2 v2 square. Now, likewise the energy 1-dimensional steady case, as we assumed in our assumptions, that h1 plus v1 square by 2 is equal to h2 plus v2 square by 2. Now, this enthalpy, the total, this static enthalpies h1 and h2 can be written, since we are talking about the rate of reactions here due to the propagation of detonation wave, can be divided into the heat of formation and sensible heat. That means, if this is the heat of formation, note that, recall from a background of thermodynamics, that the heat of formation is the amount of heat required is or released by the product or required by the reactants to form 1 mole of the product, 1 mole of the product or 1 mole of the reactants from their constituents at standard temperature and pressure. That is called heat of formation. And if we divide a sensible heat and the heat of formation as the static enthalpy, then we can write down with constant specific heat assumption something like this. And because Cpi is not changing, then this fellow can be written as total Cp T minus T naught. Now, from this equation, that is the equation number 5, let us say, introducing this in equation number 3, we will obtain Cpt1 plus V square by 2 plus complete heat addition which is occurring in the reaction and then downstream side. Note that this condition here, the heat is added by traversing of the wave inside the premixed flame structure at the supersonic speed. Now, this energy equation will now if this equation heat addition total, the sensible heat and heat of formation is written as Q, then the actual governing equation of energy equation can be written as CpT1 plus V1 square by 2 plus Q is equal to CpT2 plus V2 square by 2. Now ideal gas assumptions upstream and downstream side, that is the before the combustion is taking place and after the combustion due to traversing of travelling of the detonation wave, P1 is equal to rho 1 R1 T1 and P2 rho 2 R2 T2. Note that R1 and R2 are here the different because the gases in the reactant side will lead to the product or altogether different gases. So hence the specific gas constant also changes. Now Rankine-Hughes equation, using this continuity and momentum equation, an ideal gas relationship, that is equation of state, can be written finally something like this. But across the shock wave, since there is no adiabatic, no heat transfer is taking place and the flow process across the shock waves is adiabatic, this goes to 0 for the shock wave and then finally this first and second term remains there. That essentially bring into the form or something like this, that is P2 by P1 is equal to gamma minus 1 upon gamma plus 1 rho 2 by rho 1 minus 1 and gamma plus 1 upon gamma minus 1 minus rho 2 by rho 1. That is, this ratio of pressure across the shock waves will become a function of the ratio of rho 2 by rho 1, that is static density ratio. That means since gamma here is a short range parameter, therefore what we essentially see from this equation that it does not have the Mach number or the velocity of the flow, and this is a famous Rankine-Hughes relationship for a normal shock wave. Now in a convergent divergent nozzle, we have seen here that the shock waves are formed and we have seen that by controlling the back pressure, the shock wave can be moved out of the nozzle and convergent divergent nozzle, and whole flow inside convergent divergent nozzle will be essentially the asymptotic. Now what we see here that in this condition, when the flow is not choked, the area at the throat is always less than A star, because why it happens, because when the area normal throat area is 80 for some back pressure Pb, when the throat is not choked and the pressure at the throat is Pt, however we decrease the mass flow rate from let us say some Pb dash when the P star is taking place, and hence the area becomes A star. From this condition to this condition, the mass flow rate increases. However, when the mass flow rate increases, then based on A star, that is the flow area, the throat flow area at the throat, when the sonic condition is obtained, becomes the mass flow rate becomes maximum, and hence it denotes that in this case the m dot when the T was there is lesser than m dot star, and hence AT is less than A star, because m dot is nothing but rho area times velocity. Now similarly what we see here, that we have also seen that from this graph, that if Pb8 which is lower than Pb7 or Pb6, we have also seen that how the overexpanded and underexpanded conditions are obtained when Pb7 is equal to Pe7, that the exit pressure and back pressure are equal, then we say this is a correctly expanded flow. We have already discussed these parameters. Now what we see here, now that means wherever you require the normal shock waves must be moved out of this convergent divergent nozzle, out of the normal shock waves should be out of this nozzle, what we can see that you can always obtain for a particular P naught or a given P naught whenever your back pressure is less than PB8, which is the currently expanded pressure in the supersonic arm. In the supersonic case, isentropic supersonic flow case, then you should always have a back pressure, controlling back pressure such that it is always less than PB8, then you can obtain a shock free divergent portion of the convergent divergent nozzle, and this is called normal shock recovery. And hence P naught by PB minimum should be P naught by PB8 to have a shock free flow inside a convergent divergent portion. Assume this, that let us say writing by PO2 by PO1, that is stagnation pressure ratio in terms of the upstream Mach number which we have derived earlier. Let us say that this is 1 by lambda, that means lambda is PO1 by PO2, but for our convenience, because we know the relationship in the form of downstream to upstream cases, we say this is 1 by lambda. That means lambda is a operating pressure ratio of running this convergent divergent nozzle. Now if we have, suppose after this shock wave which has moved out of the nozzle but is still standing in the form of oblique shock waves here or expansion fans here, even though the shock is moved out of the nozzle, but if for practical application we must make it the flow outside the exit nozzle to be error free, we can do so by attaching diffusers at the exit. So now this is my second discussion where we must see what happens when a normal diffuser or a special type of diffuser called convergent divergent diffuser are attached at the exit of the convergent divergent nozzle. We will now focus into that. Thank you very much.